I'd like to talk to you about Einstein, the philosopher, and Einstein, the scientist, and about how these two aspects of Einstein were really inseparable. I'd like to start by considering a couple of questions that are kind of governing the structure of this talk. First of all, what does it mean to say we live in Einstein's universe? What characterizes the universe we live in as particularly Einsteinian? I think this is a particularly interesting question in light of the fact that most physicists today would say the correct theory of gravitation is not Einstein's, but some quantum theory of gravity of one or another sort that, perhaps down the road in Waterloo someone's going to come up with or is working on right now as we speak. And so what does it mean to say we live in an Einsteinian universe if it turns out this isn't really the final theory, which is usually how theories turn out? The second thing is, what's the connection between gravity and geometry? So one of the things I hope that you'll get out of the next little while is some appreciation of how Einstein made this connection in the first place between geometry, which had up to that time been understood as a kind of formal abstract theory. How did he associate that with something dynamical like a physical field? And finally, what's the connection between gravity and geometry on the one hand and philosophy on the other? I hope that will become clear. In other words, how did Einstein's insights into the physics of gravitation and the physical nature of geometry arise from his pursuit of philosophical problems? Well, one thing I'd like to point out that's really interesting about the Einsteinian revolution that I think isn't sufficiently appreciated is that we have a lot of questions that we ask about the universe today that really wouldn't have made any sense in a pre-Einstein context. For example, how did the universe begin? There really wasn't a theory of that in the Newtonian theory. Of course, there are previous theories of creation, but Newtonian physics didn't supply even a way of asking that question. How did the universe come to be? That's a peculiarly Einsteinian question. The curvature of space-time. This is another thing that people really didn't have any way to think about before Einstein. How does the structure of space-time vary throughout the universe? These are things that we think of as basic questions to ask in cosmology. Again, wouldn't have made any sense at all. What is inside of a black hole? These are all concepts that we consider basic to the science of the large-scale structure of the universe. All of them have to do with concepts that really came to be well defined by Einstein. This is the sense in which what Einstein did was not merely a physical theory, but a conceptual revolution. So how did all of this come to be? Well, first of all, it became necessary to think about geometry in a different way. This is what I'm contending is the primary philosophical problem that Einstein had to solve. How to think about geometry as a dynamical aspect of the physical world. If you look back through history, there are lots of conceptions of geometry, none of them quite like Einstein's. There's a very long tradition among rationalist philosophers whose names you may know. Kant, Plato, Descartes, Leibniz, people who in one way or another thought that geometry was a science that was absolutely necessary truth that had nothing to do with experience at all. Then there was another notion that goes all the way back to the ancient Egyptians and Babylonians and had champions in the 19th century like the philosopher John Stuart Mill, that geometry, the principles of geometry are basically codifications of empirical recipes for actually solving particular problems. And our confidence in them comes from the number of times we've repeated these basic geometrical operations from building the pyramids to building houses and railroads. But then there was another conception that was really quite revolutionary, which could be said to have begun with Newton, but really came into its own in the 19th century with scientists like Hermann von Helmholtz and Henri Poincaré, Carl Friedrich Gauss, Bernard Riemann. The notion that geometrical principles considered by themselves are just a kind of formal abstract structure. And that if you want to talk about geometry as the geometry of space, that is to say, as characterizing the world in some way, as describing the world we live in, you have to somehow connect the abstract mathematical principles of geometry with something physical. So there's some connection that has to be made between the laws of physics and the mathematics of space. And that was a revolutionary development that, in a way, paved the way for Einstein and made his whole way of thinking possible. But what Einstein did was something quite new, even compared to that. That is, to find a way to think of geometry not as a kind of fixed background within which the physical laws are articulated, and within which we move and measure, but to think of it as itself a kind of dynamical field, like the electromagnetic field or the gravitational field, and that interacts with other fields in nature. This dynamical conception of geometry is the basis for the general theory of relativity. But it's something that, without a kind of conceptual investigation that Einstein did, it's a concept that no one could even have understood in the 19th century, with a few possible exceptions. This is a question that Einstein asked, reflecting on the philosophical background to his way of thinking about geometry. He asked the question, how can it be that mathematics, being after all a product of human thought which is independent of experience, is so admirably appropriate to the objects of reality? Is human reason, then, without experience, merely by taking thought, able to fathom the properties of real things? In my opinion, the answer to this question is briefly this. As far as the laws of mathematics refer to reality, they are not certain. As far as they are certain, they do not refer to reality. Yet, on the other hand, it is certain that mathematics generally, and particularly geometry, owes its existence to the need to learn something about the relations of real things to one another. The very word geometry, which means earth measuring, proves this. For earth measuring has to do with the possibilities of the disposition of certain natural objects with respect to one another. It's clear that the system of concepts of axiomatic geometry alone cannot make any assertions as to the relations of real objects of this kind, which we will call practically rigid bodies. In order to make such assertions, geometry must be stripped of its merely logical formal character by the coordination of real objects of experience with the empty conceptual framework of axiomatic geometry. To accomplish this, we need only add the proposition solid bodies are related with respect to their possible dispositions, as are bodies in Euclidean geometry. This is really the key point he was trying to make. Then the propositions of Euclid contain affirmations as to the relations of practically rigid bodies. Geometry thus completed is evidently a natural science. We may in fact regard it as the most ancient branch of physics. Its affirmations rest essentially on inductions from experience, but not on logical inferences only. I attach special importance to this view of geometry because without it I should have been unable to formulate the theory of relativity. That was as clear a statement as you could get from Einstein, that he really thought that this new philosophical conception of the relationship between geometry and physics that had developed in the 19th century was fundamental to his creating the theories that he created. Although, as we'll see, he carried them to a different direction altogether. Some of his philosophical forebears you can see in this picture. Maybe I'll give you a quiz at the end, see if you can recognize who they are. If you're a philosophy professor, no telling. I'd like to begin by considering two ways of thinking about in what way is Einstein's theory part of our world. Well, you can think of a scientific theory as an instrument, because after all, if you're worried about the fact that tomorrow we might not believe this theory, what is its value? If we don't think it's really true, well, you can think of it as simply a practical tool for prediction and for the control of nature. Now, some of you probably have heard this story. There really is one technological application of general relativity that's extremely important, and it's GPS navigation. When I was in graduate school, relativity students used to say, well, we should try to convince the government that we're working on a relativity bomb, because maybe then we'll get more funding. Because they didn't come up with one, needless to say. But eventually, the GPS was developed, which is a very important application of special and general relativity, but in a way more general relativity, because you have satellites orbiting the Earth at 20,000 kilometers and at 14,000 kilometers per hour, and you have to make timing corrections for the high velocity because of special relativity, and because of general relativity, because of the difference in clock timing in stronger and weaker places of space-time curvature, you have to correct for the time speeding up. So if you subtract the time slowing down from the time speeding up, you get a delay of 38 microseconds per day, which doesn't sound like much, but if you didn't correct for this, you would have errors accumulating at a rate of kilometers per day, and your GPS navigation system would be completely off. So this is a practical application of Einstein's theory. But I'd like to think about Einstein's theory as an instrument of a different kind for a moment. That is to say, as an instrument of understanding and of exploring. Now, this is a remark that was made by Pierre-Simon de Laplace 200 years ago about Newton's theory of universal gravitation. And I think it was an interesting remark that illustrates the sense in which a physical theory, which we now regard as not true, nonetheless is an instrument for the exploration of nature like a telescope, as Laplace put it. He says the theory of gravity, having become by so many applications a means of discovery, as certain as by observation itself, has made known several new inequalities. It's enabled the mathematician to predict the return of the comet of 1759. He's been enabled by this means to deduce from observation as from a rich mine a great number of important and delicate elements, which without the aid of analysis would have been forever hidden from view. The masses of the sun, the planets, their satellites, the velocity of light, the ellipticity of Jupiter, the shape of the Earth. Now, that's a really important point that I think Laplace was making. A theory that we don't actually believe anymore has nonetheless taught us something about the universe that was otherwise hidden from observation. We know more about empirical things like the masses of the planets and their orbits from Newton's theory than we were able to tell by staring at them through telescopes. Now, if you ask, well, what has Einstein's theory done of a similar nature? Well, for one thing, one of the most familiar ideas from Einstein's theory is the theory of the black hole. The black hole, as we understand it, is a concept that really didn't quite make sense according to Newtonian theory. There was a Newtonian notion of a black hole, what Laplace and a British astronomer, John Mitchell, in the 18th century called a dark star, because they imagined that if light was made of tiny particles that must have some mass, then presumably they must be subject to the gravitational field, and there could be a gravitational field so strong that the escape velocity would be faster than the velocity of light, and they would trap the light. But it's a long time since physicists stopped believing that light was made of little massive particles anyway. In Einstein's theory, the notion that light as a massless particle can somehow be trapped around a star, or in other words, around a collapsed star or a black hole, that's an aspect of his theory that you can only understand through the notion of space-time geometry, which we'll come back to. But this is an aspect of our universe that Einstein's theory is the only theory that allows us to explore. So it's being used as a tool for the exploration of these distant objects, and there's no substitute for it. Just as securely as Newton's theory was used as a tool for exploring aspects of the universe. And this is something that bears out what it means, in my opinion, to say that we live in an Einsteinian universe, even if the theory isn't quite the right one. Another aspect is gravitational lensing, the fact that we can see, for example, stars that ought to be occulted by other stars because of the bending of light as they go around more massive objects. The simplest example of this was Einstein's prediction of the bending of starlight by the sun in 1919. But more complicated examples are things that we sometimes see in deep space photographs like this one from the Hubble telescope of the lensing of light from a distant galaxy passing around an intervening object. This is another way in which Einstein's theory is not merely a way of making useful predictions like and making a tool like the GPS. It's a way of understanding how the universe is structured. And finally, one of the most dramatic example of an Einsteinian picture of the universe that was not possible before is just the very idea we have of the history of the universe having a beginning, an expansion, and various scenarios for a possible end, which isn't coming anytime soon, I think. But these are notions that didn't really make sense in a Newtonian context. But when we say this is our Einsteinian universe, it's a universe in which we can think of it as having a kind of structure like this on a large scale. So, for example, we can ask a question which wasn't really meaningful before. What is the shape of space on a large scale? If you consider a slice of space-time, right, a large slice of the universe, what is its spatial structure? Is it curved like a sphere? Is it curved like a saddle? Or is it flat? Well, these weren't even interesting, they weren't even possible questions to ask before Einstein made the philosophical effort to figure out how such questions could make sense. Now, how did Einstein get started on this path? He started with a simple question that he got from reading works by Ernst Mach, a 19th century physicist whose name you might know from The Speed of Sound. How do we really know that the Earth is rotating instead of having the stars revolve around it? Well, Newton found a way to settle this question in 1687. We know the Earth is rotating because it bulges out at the equator and in various other ways displays centrifugal effects. By the 19th century, the end of the 19th century, when Mach wrote this book on mechanics, there were further proofs like the Coriolis effect, the Foucault pendulum, demonstrating the rotation of the Earth. But Mach asked the question, do we really know from these effects that it's the Earth rotating relative to the stars, or the stars rotating relative to the Earth? And there's a lot of philosophical mystification about this idea, but part of, I won't read the entire quote to you, part of what Mach had in mind was a simple application of the experimental method. If you'd like to be sure that it's the Earth's rotation and not the star's rotation that's creating the centrifugal effects on the Earth, you ought to be able to vary, as a matter of experimental method, you ought to be able to vary the two things separately. Do we know what would happen if the stars rotated around the Earth? Well, of course, we don't know that because, as Mach said, the world is only given to us once. The Ptolemaic or Copernican system is our interpretation, but both are equally real. So the Earth is not given to us twice, once with an Earth at rest and once with an Earth in motion, but only once with its relative motions, which are alone determinable. Therefore, we cannot say how it would be if the Earth did not rotate. We can interpret the one case that is given to us in different ways. If, however, we interpret it in such a way that we come into conflict with experience, our interpretation is wrong. Now, when I wanted to read the original edition of this book, the only place I could find it was in the Bertrand Russell archive at McMaster. So it was Bertrand Russell's copy, one of the great philosophers of the early 20th century. So I read this remark, the universe is not given to us twice, and we cannot say how it would be if the Earth did not rotate. And Russell had written in the margin, rubbish. And because what he meant by that was, of course you can say what would happen if the Earth didn't rotate but the stars did, because you have Newtonian physics. It tells you what would happen in every conceivable situation. Any kind of You just tell Newtonian physics what the matter distribution is and what the forces are, and it will tell you what will happen. But Mach's point was, we don't really know if these are the laws of physics. At least this is the philosophical notion that Einstein got. We could be skeptical, since we don't know what would happen in these other situations, we don't know if we have the right physical laws now. So when Einstein looked at this situation and said, suppose you have two spheres rotating relative to one another, and one is bulging out at the equator and one isn't, how do you explain the difference between the two spheres? And his answer was, well, the only epistemologically satisfactory answer has to be something that points to facts of experience. Newtonian mechanics does not give a satisfactory answer because it says the laws of mechanics apply to the space R1 in which the body S1, the spherical one, is at rest, but not to the space R2 in which the body S2 is at rest. But the privileged space R1 is a merely factitious cause. So he's applying a philosophical principle here to say the Newtonian laws of physics probably aren't the right laws because they have this philosophical difficulty that they're appealing to something unobservable. Instead of explaining the effects of rotation by visible causes, by observable causes of some kind. The only satisfactory answer, according to Einstein, is that the physical system reveals within itself no imaginable cause to which the differing behavior of S1 and S2 can be referred. The cause must lie outside the system, in the distant masses which we haven't been considering. Excuse me. These distant masses must be regarded as the seat of the causes, which must be susceptible to observation of the different behavior of S1 and S2. They take over the role of the fictitious cause, R1, in other words, the space. Of all the imaginable spaces in any kind of motion, there is none which we may look upon as privileged a priori without reviving the above-mentioned epistemological objection. The laws of physics must be of such a nature that they apply to systems of reference in any kind of motion. Along this way, we arrive at an extension of the postulate of relativity. In other words, Einstein knew that in Newtonian mechanics and in special relativity, there was a relativity principle, that whether a system is moving uniformly or at rest is a completely relative matter. But what about systems that aren't moving uniformly, systems that are rotating or accelerating? Why are they supposed to be different? Again, it was a purely philosophical problem, and there's a great deal more to it than I can go into this evening. But the important thing is that Einstein thought it was odd for the theory to single out certain kinds of coordinate systems or reference frames, because he asked the question, well, why should nature care about our coordinate systems? Why should there be infinitely many inertial systems moving uniformly that are distinguished from all other rigid systems? Now, people had been asking this question for hundreds of years in various ways. The real interesting thing is, why in Einstein's case was this philosophical problem made into a real line of physical inquiry that actually led to a new theory? I'll skip that one. Let me start by considering the idea of an inertial frame. If you haven't heard the term before, it won't be very hard to figure out. If you were sort of enclosed in a box in empty space and no forces were acting on you in any way, you would be in what Newtonian physics or special relativity would call an inertial state. So imagine you're in a box, there are no forces, but you're somewhere far from, as far as you like, from all possible matter. You're just floating around in a way that might look familiar to you from, say, space capsules or orbiting space stations. It would be as if no forces are acting on you at all. Now, Einstein considered this other possibility, however. What if that same box were falling in a gravitational field? Well, because of a peculiar fact about gravitation, you wouldn't be able to tell the difference between being in this box, falling in the gravitational field, and being all alone in empty space with no forces acting of any kind. Some of you may have heard this before, Einstein's elevator argument. He was the first person to really consider the implications of this problem, that an inertial frame of reference is impossible to distinguish from a frame of reference that's falling. Now, why is that the case? Because of something that was discovered by Galileo, that gravity has the same effect on all bodies near the Earth. So if I'm falling in a gravitational field and I pull a couple of bowling pins out of my pocket, or a ruler, or a grapefruit, or whatever I've got in my pockets, they're not going to fall any slower and faster than I am. So I won't notice that I'm in a gravitational field. I won't feel the top of my body weighing down on the bottom of my body. It will all be the same. It will be as if no forces are acting on me at all. This is why astronauts in orbit feel weightless, because the same force is acting on them and all the parts of their body and everything else in their shuttle. Now, if you imagine a similar example where you have the same box, but now it's sitting on the Earth. Now, of course, the man in the box feels his weight on the floor. He lets go an object, it just falls to the ground, 9.8 meters per second. And he has to make some effort to hold that bowling pin up. Right? Now that seems pretty obvious. But now imagine Einstein's evil twin. It's his brother Frankie, the one nobody talks about. Now, the evil twin is in a very similar box, but the box starts being pulled upwards. That's totally wrong. Well, Einstein's evil twin at work. The point is, if the box were accelerating upwards, you would feel the exact same effect, because your inertia would be holding you back while the bottom of the box is pushing you upwards. If you were accelerating at exactly the opposite of the Earth's gravitational field at 9.8 meters per second in the opposite direction, then you would feel exactly the same thing you'd feel from your weight on the floor. So in other words, the inertial effect of having the frame of reference of the box that you're in accelerate upwards is the same as the gravitational effect of having your weight pull you down. Just as the effect of being an inertial frame with no forces acting on you is the same as the effect of falling in a gravitational field freely. Now, what does all this mean? Well, it doesn't necessarily mean anything new. Right? Einstein said, well, it's clear that you can't distinguish gravity from inertia, because to the observer in the box, if the box is at rest in a gravitational field, it's not clear whether you're sitting in a gravitational field or the box is being pulled up. And it's not clear, there's no way to tell from an experiment whether the box is falling in a gravitational field or being acted on by no forces at all. But this isn't by itself a really strange idea. This is an idea that Newton had. There's the relativity theory of Newton's Principia, as stated in these corollaries that he derived from the laws of motion. First, he proved that the bodies contained in a given space will have the same motions among themselves if the space is at rest or moving uniformly. This is the Newtonian principle of relativity, derived from Galileo and Huygens, but expressed in this form by Newton. But Newton pointed out this more radical step, that if bodies are moving in any way whatsoever among themselves and are urged by equal accelerative forces along parallel lines, they will all continue to move with respect to one another in the same way as they would if they were not acted on by those forces. So Newton already understood that if you have a system of bodies that's falling in a gravitational field, it will behave exactly the same as if it were at rest. You might wonder, why was Newton worried about something like that? And the answer is, he was concerned about understanding things like the system of Jupiter and its moons. Can I analyze the system of Jupiter and its moons when the whole system is being accelerated toward the sun? And the answer is, yes, I can, because the actions of the sun on Jupiter and its moons because they're so far away from the sun, they're almost equal and almost parallel, and you can treat that system as if it were at rest. Now, what about the whole solar system? Newton has a very detailed argument for universal gravitation. Would that argument be undermined if you found out that the whole solar system is falling in a larger gravitational field? And the answer is, because of corollary 6, no. It would behave exactly the way it does now as long as the accelerations caused by that distant mass, whatever the whole solar system is falling towards, as long as those accelerations are nearly equal and nearly parallel, we're not going to notice them. So the basic idea of gravitational free fall producing this kind of relativity of acceleration is something that goes back to Newton, and it doesn't have to have the kind of far-reaching implications. It doesn't obviously have to have the kind of far-reaching implications that Einstein saw. There he is again. But why does it have these applications? Now, if you consider, why does it have these implications? Excuse me. Consider Einstein again and his evil twin, and they're both thrown off of the Chrysler Building in their little frames of reference. What happens? Well, as far as Einstein is concerned, he can consider himself as being in an inertial frame, and he can consider the path of his little box as nothing but an inertial trajectory of a body not being acted upon by force. He can consider himself as an unaccelerated body. But what about his brother? He will feel the same way, because he'll have the same effect of being freely falling in a gravitational field and not experiencing any acceleration. But when they observe each other, each one will look at the other and say that they're accelerating, that the other is accelerating. Because relative to Einstein, relative to Albert Einstein, Frankie is accelerating and vice versa. So if you consider, in special relativity, locally you could always feel like you're in an inertial frame, but if you look at another trajectory, if it's falling in a gravitational field, it might look like it's accelerating. Now, how does that lead to a new kind of physics? Well, Einstein first had to make this conjecture that absolutely nothing in physics would ever make a distinction between freely falling and being in an inertial state. If there's anything you could do, any material, for example, that didn't respond in the same way as everything else to gravity, right, then this whole theory wouldn't work. See, Newton's theory, Newton didn't really know what the nature of light was. He didn't know how light would be affected by gravity. So he didn't know how far this principle might extend. So, for example, if you tried to trick somebody into thinking there was gravity with a magnetic field, right, well, the person could always use pieces of wood that aren't falling in the magnetic field, right, something that's not magnetic, to prove that it's not really gravity. So this is why Einstein said, if there were just to exist one single thing that falls in the gravitational field differently from all the others, then with its help the observer could recognize that he is in a gravitational field and is falling in it. Right? If such a thing does not exist, however, as experience has shown with great precision, then the observer lacks any objective ground on which to consider himself as falling in a gravitational field. He has the right to consider his state as one of rest and his surroundings as field-free. But this is where this physical fact about gravity connects with the philosophical argument that he made before, because he says the experimental fact that the acceleration of fall is independent of the material is a powerful argument that the relativity postulate has to be extended to coordinate systems which, relative to each other, are in non-uniform motion. I'll skip that one. But you can make a comparison to the curvature of the Earth. You could imagine a small piece of the Earth where you're standing and thinking, this is a flat plane. If I could just extend this plane forever, I would see that the Earth is flat. If I raise a flagpole here, it's perpendicular to the surface of the Earth. But of course, somebody somewhere else can say, If I raise the flagpole here, it's perpendicular to the Earth. How is it possible to fit these two non-parallel flagpoles into a system in which they're both perpendicular to the surface of the Earth? We'll come back to that. Einstein's answer to this is something that he called the geodesic principle, that we now call the geodesic principle. If the path of a falling body cannot be distinguished by any evidence from the path of a body that's subject to no forces at all, then the path of a falling body is physically equivalent to something moving into the path of a body that's moving inertially. This means that just as we can interpret straightest lines on the Earth as geodesics, or lines of longitude, we can associate the straightest lines that you can fall on in space-time with the paths of falling bodies. I'll try to make this a little bit more pictorial. Right, the Newtonian view was, well, a body is in orbit because there's a force preventing it from going off on the tangent. So if you ask, what's holding a body in orbit? Well, if it were moving inertially, it would move on this geodesic track G. But in fact, there's a force binding it in orbit, and that's why it goes around the sun. If you imagine this as going forward in time, right, with space horizontally and time moving upwards, right? As time goes on, the revolution of a planet around the Earth is this kind of helical path. Now, if you imagine two separate particles falling in the Earth's gravitational field, right, falling toward the center of the Earth, how should you interpret that fall? Well, Newton would say, if they're following the straight lines of space-time, the inertial trajectories G, the force will make them withdraw from those inertial trajectories and fall toward the planet. Now, Einstein says, well, there's no way to distinguish the actual path of the falling body from an inertial path. So these straight lines are purely imaginary. We don't have a physical way to distinguish those. So we have every right to say that the paths of these particles that are accelerating toward the Earth really are the inertial trajectories of space-time. So you could look at this in terms of coordinates. You could say, well, in my coordinate system, you're accelerating. Right? You should be moving on this straight line G, but in fact some force is causing you to move in a curve. My equation of motion is, well, the acceleration is zero because I'm an inertial observer. And I think your equation of motion is, well, you have this acceleration that's proportional to the gravitational potential. But of course, if you think back to the example of Einstein and his brother, well, Einstein's brother has the same right to say, no, I'm in an inertial trajectory, my acceleration is zero, you are accelerating. I'll skip that one. Now, what kind of a world is it where two observers are moving inertially, no forces are acting on them, and yet they accelerate toward one another? What kind of a world would that be? Well, it's just a kind of four-dimensional analog of the surface that we live on. If two observers start from the equator moving in lines that are perpendicular to the equator, and they move in straight lines, as straight as they can, using for maybe a compass or an inertial guidance system even. Well, if they follow the straight lines of the Earth, the lines of longitude, they're going to find that they accelerate toward one another. They converge on one another uniformly at the North Pole, if they happen to be going north. And that's exactly what's happening in this example, right? In this case, we say, well, this is a bizarre thing that wouldn't have happened if the Earth weren't a curved surface. And Einstein's point was, this is a bizarre thing that wouldn't have happened if space-time weren't curved. The trajectories of inertial observers in space-time have the same non-Euclidean behavior indicating curvature that the straight lines of longitude on the Earth have. that indicates the spherical shape of the Earth. And this is that connection, finally, where we've gone from a philosophical idea to a physical idea about gravity to a radical new idea about geometry. But the thing about geometry is, what's radical about this idea is, geometry is related to gravity. But gravity isn't something that's fixed, as geometry was supposed to be. Gravity is something that varies through space-time according to the distribution of mass. It's very powerful near a very massive object. It's weaker near a weaker object. Now, if gravity is the same as space-time curvature, then that means we've taken a dramatic step. We've found that the actual geometry of space-time varies according to the distribution of mass. That makes geometry, as I suggested at the beginning, it makes geometry something that it never was before, a kind of dynamical physical field whose changes depend on the distribution of mass. Newton would have told you, well, the gravitational field that forces bodies not to travel in straight lines is determined by the distribution of mass. Einstein says, well, that's the space-time curvature, the way in which straight lines accelerate toward one another. That's an indication of the distribution of mass. Well, of course, mass energy in the relativistic context. There's a common empirical basis. What are we observing? We're observing how inertial trajectories accelerate toward one another, how the paths of falling bodies accelerate toward one another. We're just interpreting it in two ways. Newton interpreted it as a field that's causing bodies to deviate from their straight line motion. Einstein interprets it as the geometry itself being affected by the presence of mass. Now, some people call that geometrizing physics, but that isn't how Einstein thought of it. Einstein thought of it as physicalizing geometry, making it into something dynamical like a physical field. Now, this takes you back to Einstein's remarks about coordinates, right? The method hitherto employed for laying down coordinates in the space-time continuum thus breaks down. I won't read all of this. There's no way, but what he means is, if you think about classical space-time, right, or a flat coordinate system, if I thought the universe was flat, I could imagine that my coordinate system, as on the far left of your screen, was simply a flat coordinate system that could be extended infinitely in every direction. But Einstein introduces this idea, instead of a reference frame that's rigid, like a Cartesian coordinate system or a plane, something that's kind of wiggly and squishy, like a mollusk. And so when you have two observers who locally feel like they're on a flat plane, but if you try to you can't fit them both into a larger frame in which they both fit into the same flat plane, this is the situation you have with inertial observers falling in general relativity. That you have Einstein and his brother locally, it's as if they're in flat Cartesian coordinates, but if they compare each coordinate system to the other one, you find, well, the simple idea of coordinates doesn't work anymore. The idea of extending a coordinate system to the entire universe, or even to a very large area of the universe, just breaks down. So this is how all of Einstein's ideas come together in this. Starting with the philosophical idea, well, there's something wrong with the idea of a rigid rest frame, a flat coordinate system that sort of characterizes the entire universe, is privileged, is separate from all physical interactions. There's something wrong with the idea of an inertial reference frame being distinguished from all others. Those were initially just philosophical ideas, but it was this peculiar feature of gravity that it enables you to treat a system that's falling in a gravitational field as if it were moving uniformly in a straight line, because locally you can't tell the difference. So that was a physical reason to take this old philosophical idea and say that it actually has physical content that has to do with gravity. But this physical content is the key to uniting gravity with geometry and showing that if you want a coherent picture of the reference frame of one inertial observer and the reference frame of another observer who's equally inertial, but relative to the first one accelerating, then there simply isn't a flat coordinate system into which you can fit them both. The only system in which you can fit them both is a curved geometry. So that's a rough sketch that I hope conveyed something of the philosophical path that Einstein took from a combination of philosophical problems that he found in the existing physics, facts about gravitation that he thought were never really quite understood properly in the Newtonian theory, and a new conception of how the relation between physics and geometry can be explored and developed. And in a sense, that's general relativity in a nutshell. That's why the talk of curved space-time is meaningful. It's meaningful in the same way that talking about the Earth being curved is meaningful, because we can follow straight lines on the Earth and we know that their convergence indicates the curvature of the Earth. We can follow inertial trajectories in space-time and say their funny converging and diverging behavior indicates the curvature of space-time. Now that's a remarkable philosophical achievement, and you might think it would be a terrible thing to throw this away just because we need to have a quantum theory of gravity, and maybe the quantum theory of gravity won't incorporate these great ideas of Einstein's. Now you could just adopt a definition and say, well, if the next theory doesn't include these great ideas, then that means they weren't so great. You don't have to think about it that way. There are probably more than three ways, but you could consider these three ways in which a theory can survive after physicists have decided that some other theory is more correct. Now, the obvious one is, of course, a useful tool for making predictions and for practical applications. I mean, lots of old theories are still good in this way, especially Newtonian gravity. Another way that's a little bit more serious for a theory to survive in a future theory is for it to be a limiting case of the theory. So we say of special relativity, well, that's actually what the world looks like in very small regions, even if general relativity is true. It's a limiting case in which you consider very relatively small masses, and therefore nearly zero curvature. Or Newton's theory related to special relativity. It's a theory you have when you consider very slow velocities, and relative to which the velocity of light appears infinite. But another way you can think of a theory surviving is when the theory can still be regarded as a source of insight into the way the parts of the physical world are connected with one another. And that, I think, is certainly true of Newton's theory of gravitation, but it's even more true in a sense of Einstein's because of the remarkable connections that his theory has revealed. Some of the things that I mentioned at the beginning of my talk. We understand things about large-scale structure. This is a famous remark by Henri Poincaré about this very question. He says, of course, it seems to us that theories only last a day, and that ruins upon ruins accumulate. Today, theories are born, tomorrow they're the fashion, the day after tomorrow they're classic, the fourth day they're superannuated, and the fifth they are forgotten. But if we look more closely, we see that what thus succumb are the theories properly so called, those which pretend to teach us what things are. But there is in them something which usually survives. If one of them taught us a true relation, this relation is definitively acquired. It will be found again under a new disguise in the other theories which successively come to reign in the place of the old. Now let's think about general relativity. Well, of course, it's the most empirically successful theory of gravity. Its predictions will probably continue to be useful, at least as long as people continue to use GPSs. It'll be an easier way of doing that probably than any quantum theory of gravity, which is likely to be highly complex. And it's likely to be a limiting case for a future quantum theory of gravity. But I think at a deeper level, it's a unique and indispensable window into physical connections, even on the very largest cosmic scales, which no previous theory gave us any inkling of. Large-scale cosmic structures in space, that is to say, considering just the spatial part of the universe and its curvature or flatness. In time, just considering the evolution of the universe from what seems like a beginning to what might be an end. And space-time, the combination of the two. And one more thing that has to be said, I think, and I hope I've convinced you of, is that the general theory of relativity is not only those three things, but it's also clearly a product of Einstein's critical philosophical analysis of established conceptions of gravity and geometry. And that's why we celebrate him as a philosopher scientist, and that's why we'll continue celebrating that all this year. Thank you very much for listening.